Hello folks, this is tutorial number 10 in the playlist that are called Transitioning to 3D Experience from the ABAQUS CAE program. It involves a buckling problem of an open profile beam. And it is taken from uh, the work of the video of Dr. Wagner, where the same problem is done is in its entirety by the ABAQUS AE program. So we have an open profile beam as shown here, and it is simply supported at both ends. The dimensions are given here, and the thickness of the sheet metal is 2 millimeters. We're going to do a linear buckling analysis. And once we find the buckling load factor, then we're going to run the same thing under a linear static analysis and compare the results with a source that we have. And eventually we're going to do that as a nonlinear problem. Here is the same drawing to scale. This is drawn to scale. And it's going to be meshed with S4R elements, 2 millimeters in size, roughly 2 millimeters in size. Left side is entire four edges is simply supported, no translation. And same thing on the right, except that it's being pushed by a dummy load of 1 Newton per meter, or sorry, 1 Newton per millimeter. Now, when you run this thing to get the buckling load factor, there will be an error message saying that one has to increase the number of iterations, and I can change it. I think the default is 30. I changed it to 100, and it ran fine. The theoretical solution that the YouTuber is looking at is from this reference, and for us, based on the dimensions that are given, this ratio C over B is almost 0.6. Well, it's 0.625, so it's roughly there, and the B over H is 0.5. That means that the particular value that we read of this thing and we have to compare it to is 33 actually. This number, if you this horizontal line, if you continue it, the red line is going to intersect the vertical axis as 33, and that 33 is this ratio. So when you set this ratio equal to 33 with all the dimensions that are given, you'll find the critical stress based on this linear analysis from that reference. We get roughly 822 megapascal. So once we have our buckling load factor, we're going to use that load factor to apply an edge load, and that should give you, for linear analysis, it should give you roughly that stress. The midsection. All right, let's go ahead and do this problem. Remember, we're using 3D Experience Release 2024. So on that vertical axis, that vertical plane, I'm going to sketch that shape. The shape is like so. I'm going to clean this up in a minute. Okay. All right. Now, I don't want these things to snap to grid points. So when we get there, we're going to deactivate that. Okay. Okay, so let's see now. These dimensions, first of all, they're drawn symmetric, which is good, but these dimensions are that uh, this is 80 millimeters. So let's get this thing dimensioned. 80. It's fine. And this height is 25. 25. And this one is 25. Is also 25. Okay. Oh, these flanges are 25. Sorry, these things are 40 actually. 40. So is this one. And these dimensions are 25. So this flange is 25, and so is this one. Okay, so exit, and I go to surface and extrude that by 300 millimeters. Okay, good. Then we're going to apply material to that. So let's go to tools, create a material. This is January 12, 2024. It's a steel, basically, linear elastic property for steel. All right, so it's right there. So apply. I'm going to close that, apply it to this part, and we input a value. So double click on this. So under structures, ABAQUS multiphysics, mechanical, elasticity, elastic, it's not this, elastic, that. Elastic is 208 GPA, 0.3 is Poisson ratio. Okay, so that takes care of this. Now let me hide the sketch here. Let me hide the sketch. All right. So now we're going to go to meshing, the meshing tool, the meshing application, which is a structural model creation, MTFEM. And then under the meshing, we're going to use the quad mesh, surface quad mesh. That is the surface, and the size is 2 millimeter. So there we are. It's a very fine mesh. That's fine. And then we're going to go apply the properties. So under the properties, select the shell section, select the surface, okay, and the thickness of this is 2 millimeter, and it's the middle surface, so I don't have to change any of these things. Oops, yeah, I don't have to change any of these. It's already default. Say okay. All right. Now we're going to go to uh, what is that? Structural scenario creation. Let's do a buckling first. So we go to select the mesh, select the finite element model. Okay, to make my job easier, I'm going to right click the do a visibility manager, and let's hide the mesh. There's the part. Okay. First thing, we're going to apply a procedure, and the procedure is buckling. So there's the buckle step, and this is the number that I have to change, otherwise I get that error message. Remember I said that with the with the default of 30, I get an error message. So what I'm going to do is I'm going to change that thing to 100. We say fine. This end is simply supported, so we go to boundary conditions, select the fixed displacements. So this edge and that edge, vertical edge, and this one, that vertical edge and this horizontal, is a pin, so simply supported means no translation XYZ. On the other side, it can move in the X direction, so we do the same thing. except that when it comes to fixing, we're going to leave X, displacement X alone. So it fixing Y and Z, and that's pretty much it. Okay. And for the load, we apply a dummy load of 1, but we use a shell edge load. And I have changed the unit so that it's Newton per millimeter. So I'm going to select this edge and that edge and that edge, this vertical edge and there. So we put down a dummy or reference load of 1 Newton per millimeter. Okay. And let's do a save here, quick save. Notice that here in the tree, we have a step or procedure, and that procedure is or a step, and that step is buckling step. Right. Let's run it. We go to simulate. Let's do a quick model and scenario check to see if we get any obvious error that we can fix before we run it. No problem there. And then we do a simulation check. Ordinarily, when you do buckling problem like that, now those edges on the right side and the edges of the left side are assumed to be associated with the reference point, and then apply the information on the reference point, as I have done in many other videos that is in this playlist. But here, I'm following exactly the steps that Dr. Wagner in that YouTube video on CAE's fault is doing, so I'll use just points, not reference points. Okay, so now we're going to run it. Remember, the purpose of these videos is to take examples that are done entirety in ABAQUS CAE and replicate the steps in the 3D Experiences platform. This is for people to see and appreciate the differences in the interface and some of the functionalities. Although the FEA solver buried in 3D Experience is the ABAQUS program. All right, this is going to be fairly quick. We're extracting 10 buckling values, except that the first one is the one that really counts. Relevant, actually. Okay, so you can see that the load factor is 1,231, 1,231 point roughly 46. The 46 doesn't matter here. So we're going to take this thing and apply it to as in our linear static problem. Incidentally, you can see here, for example, this is the deformation, this is the displacement. That's the first buckling load, and then as you go walk your way through, the buckling of the flanges are going to pop up, etc. We were just interested in the first one. Now we have two choices. Now that we know this number, I can completely delete this buckle step and do a linear static one. Or I can add it after that. The only thing is that when I run it, uh, I don't want this thing to run. So what I'm going to do is the following. I'm going to go here, go to scenario, right there. I'm going to delete this. And when you delete it, obviously everything goes with it. So now we're going to go to procedure, static step. Now, if you're going to do linear static step, when I do this, I have to go and uncheck. I have to go and uncheck the NL geom. And If that is the case, then instead of doing this, why don't we do the linear perturbation step, static perturbation step? Because that's the same thing. This is the same as that when there are no nonlinearities, okay? So I'll go to static perturbation step. We say fine. And now we're going to go and add the boundary conditions. So boundary conditions are exactly what we had before. On this side, these edges, you can see why it's a good idea to create a reference point, because then we don't have to apply to all these edges. We just apply to the reference point, and then we say okay. And same thing on this side, except that it can translate in the direction x. Fix in y and z. And for the load, we're going to apply edge load of the magnitude of that factor that we got. So this edge, that edge, this edge, over here, and over there, and it's going to be that buckling load factor, which is 1231. 1231. I dropped those decimals, so that's fine. Now we're going to run. So let's do a model check. So a simulation check. Again, I don't anticipate any problems. And finally, when this finishes, assuming there are no errors, then we're going to run it. And when we check our stress in the middle section of that folded sheet metal, we should come up with something close to that number that we have from the indicated paper. Okay, now we're going to run it. So linear analysis is going to go very quickly. You can always, there are no iterations here, so really it's going to be two increments, one increment actually. You say fine. Okay. So as far as displacement goes, this is the displacement, except that, you know what I'm going to do? I'm going to increase the scale here, because if there's any buckling, it doesn't show there. Okay, so let's go ahead and do the following. Double click on this. Go to the last, go to the middle tab. And for scale factor, oh, it's already 33 times bigger. Okay, so let's actually make this thing 100 times bigger, see if it makes a difference. So it's compressed more, you can see that. But because we are doing a a linear static perturbation, we don't see that bulging effect. So let's do the following. Let's plot the von Mises stress, and it is difficult to see it here because remember, this is less than the buckling load. But what I'm going to do is I'm going to click on there and go to the first tab. Von Mises stress. I don't want von Mises stress. I want the stress in the direction 1, which is x, and say apply. And if you put the cursor here, if you this thing out of the way, let me say okay. If you put the cursor here, it gives you the value of the stress, axial stress, which is roughly 614 in the middle, 615, 16, and this unit, of course, is a Pascal. So in megapascal, it's 615-ish compressive, and that agrees with what we have here. that number should be compared with this. Okay, so now what we're going to do is we're going to say, fine, we don't want this linear static perturbation. I'm going to delete this. Let me go back to the scenario. I'm going to delete this, and I'm going to add a nonlinear static step. So you click on it. The only thing I'm going to do is these numbers, I'm going to change to 0.01. Are you the same numbers that the fellow in Germany is doing, 0.01? And notice that by default, fix that, 0.01. Okay. Notice that by default, the nonlinear geometric effect is on. If I was using this in the last run, in the previous run, I would have deactivated that, but that becomes equivalent to the static perturbation. So we say, okay. Now, because I deleted my previous procedure step, all the boundary conditions are going to be gone. So boundary conditions, fixed displacement this side. There are more efficient way of selecting these things. So X, Y, Z, say okay. And then another one on this side, this edge and that edge, over here, over here, over here. It can move in direction X, but not in Y, and Z. And for load, I will apply that same edge load, that factor that I got. Right? So this edge and that edge over here, over here, over here, and the value is 1,231. This is my load factor from the buckling analysis. And now we're going to run it. Let me do a quick save here. I'm not going to bother doing the model check and simulation check. I'm just going to run it. Because we make the step size smaller, initial increment smaller, give it the maximum increment of 0.01, you'll see many increments, and up to a certain point there's no buckling, of course, and then beyond that, beyond a certain point, there will be buckling. Okay, and of course the buckling is going to be in the web and the flanges. It should be consistent with that theoretical value that you got, and that theoretical value is for linear analysis. So this is not going to be the same number. It's going to be, you'll see that it's going to be lower. And you can see that this is doing iterations now because it's solving it as a nonlinear problem. But it's a fairly straightforward one. When this thing gets down to 1, then it's all done. Right now it's 30%. Keep in mind that when you apply a load and you increase it, it doesn't buckle right away. But the whole point is that there reaches a point where this compression actually turns into buckling of the flange and the web, different section. When you take a beam and you compress it, initially just compress it. Then when the critical load is reached, then that thing goes out, kind of. We're up 70% complete. By the way, you can plot the progress of this thing too, but this, remember, it's equivalent to the monitor key in the ABAQUS program. Once you submit a job, you can say monitor, it'll tell you how far you've gone in the analysis. Ordinarily, one plots the force versus deflection. In other words, for example, how much force applied versus the reaction versus the displacement. But I'm not going to do that. It was not done in that other YouTube video, and then I'll just leave it out. It's almost done. Yes. So we close that. And now you can see the buckling mode, different buckling modes. Okay. So initially, of course, there's just compression. There's no buckling. But when it gets close to that buckling load, you see that patches kind of begin to appear at lower than what the final value is right there. Okay. And here, because it's nonlinear analysis, if you double click on it, you can change the scale from 1 to, let me make it 30. Apply. And you can see it. Okay, maybe even make it higher, 60. Okay. And this, of course, is the value of these are the, the stress contour, this, the component in the direction X, which is really what you want. But let me put this thing back to, let me put it back to 1. And use the cursor to see what is the stress value in here. So it's going to be, you'll see it's going to be lower, lower than that analytical solution, which was 620 to 23. And this is consistent with the result of that YouTube video using CAE. All right, folks, good luck.